Okay, good afternoon and good morning and good evening. So welcome to the 51st ASE seminar. ASE stands for Advanced Supercomputing Environment. Actually, so we have a 50th ASE seminar next week, but so please don't be confused. So I will briefly overview the history of this seminar. This seminar was started so 16 years ago, March 2008, by my former colleague, Professor Takahiro Katagiri. He's now in Nagoya University. So this seminar is held irregularly. Usually when we have domestic international visitors to our center, so we host this seminar. Okay? And the official language is not fixed, but today it's in English. Okay? And so any topic related to HPC and supercomputing. And the last meeting before COVID-19 was the 40th on February 4th, 2020. And after that, we have a long break. And we have one online meeting during the COVID-19. But we started this style of the hybrid meeting from April 2023. Okay. So today, we have two excellent invited speakers, Richard Graham from NVIDIA and Takeshi Nandi from Kyushu University. Okay. So this is the agenda, and we have invited talks. And after break, we have related talks from our faculty members, including me, and finish the seminar. Okay, so let's go to the first talk by Rich Graham from NVIDIA. So I'll briefly overview his profile. So he's a senior director, HPC technology at NVIDIA's networking business unit. And his primary focus is on HPC network software and hardware capabilities for current and future HPC technology. Before joining Mellanox and NVIDIA, so he spent 13 years at Los Alamos and Oak Ridge, so DOE laboratories. And he's a co-founder of the OpenMPI collaboration and was chairman of the MPI 3.0 standardization effort. Okay, so please join me to welcome our keynote speaker.
So, sorry again for the long delay here. Thank you very much for the invitation to come and talk. What I thought I'd talk about today is a topic I know there's at least some interest in it in the room here, around the area of using the various ways to offload things related to networking, to communication, to the network. So this is what I thought I would talk about in this meeting. So the focus of the actual technical, a lot of the technical details that will be talked about relate to the blue field, but the ideas are a lot more general than that. And so I'm sort of trying to put that in that context. And so I guess a first question that really needs to be asked is why do you care about, why do you want to offload things from network related activity, for example, from the main processor, from the main CPU to some other device? And ultimately the question is, the answer, at least in the context that I'm focused on, is you want to make the applications run faster. That's really why you do this. And so at the end of the day, you would like to see graphs like this where, on if green represents running the application in traditional mode, these are all recorded in times. Blue represents some sort of additional capability that you introduce to the system. You would like, at least we would like to see the times for the applications to run down. I think to go down. I think that's often the target for people, at least in the area of HPC, in terms of why we do these sort of things. So this is independent of what you do, but this is really the goal. And so in our context, the context that we worry about, it's really around offloading communication progression and the like, to the way offloading it from the entities that do the compute. So if you look, here's sort of a cartoon of the way most of us look at parallel systems. Sorry, I've been losing my voice, so I need to think periodically. on the left-hand side here, we have the traditional view of what a server would look like, where you have your compute engine, your host, whether it's CPU based, GPU based, FPGA, whatever it might be doing, that does everything. It even manages a lot of, it runs the application, but simultaneously it needs to provide a variety of services such as storage, communication management, security, a variety of things. And the network has typically been sort of an attachment to the system. Right? Some of them do more than the others, but it really has very little to do with a very, very small role aside from moving bits around, basically. Traditionally, that's the way it's. That's not completely true, but at a very high level, that's close enough. But one of the things that's very attractive, and this is a slide here that describes what we do with our data processing units, our DPUs, is the goal with those type of devices is to move some of the services away from the host to be able to do two things. Well, in the context of HPC applications or AI applications, the focus is really to let the host be used mostly for what it was designed for computation, and then move other services away from the host. So you have these very expensive server processors or GPUs or whatever. You don't really want to use them and take advantage of only a fraction of their computational capabilities while you're idling the rest of the resources, so you can do some sort of IO related stuff, storage related stuff, security, things like that for other services. And so this is really a motivator to one of the motivators, not the only one, to move to a design like this. And so as I said, all the examples I'm going to talk about, or most of the talk is going to be about what we've done with our Bluefield unit in the context of HPC applications. And this is actually most of the data I'm going to share was from a paper we published at ASE this year, precisely about offloading, particularly collective operations to the DPU. So just for those of you that don't know in the room here, what is NVIDIA's DPU? So I have a cartoon here and a bit of statistics. On the right hand, or a bit of information. On the right hand side, we have sort of a cartoon of what the DPU is, the data processing unit is, a very generic cartoon. So generally, what it has, generally it has so first of all, the DPU is a socket on a chip, system on a chip. I'm sorry, where it has in it. Part of it is a ConnectX core, that is the network, the core that drives the interface with the network. But it also has on it programmable ARM cores. The number and the type differ based on generation. In addition to that, there are it also has its own memory subsystem, its own DIMMs and the like. So it has capabilities to be able to run workloads that are independent of what happens on the host. Just like in any parallel application, the reason every CPU is doing the same thing is because that's how application programmers write code, right? Code that's replicated and run on different CPUs. Here is the same sort of idea, but what you would run there is probably not the same thing that you run on your main host. And that's how one of the ways you could use this. There are other features about this that are less important. This device was originally designed for storage and for virtualization support. So there are other optimizations aimed at that system. So from a generation perspective, Bluefield 3 is a current Bluefield device. It's an NVR, or 400 gigabit per second nominal bandwidth device. It has Bluefield 3 has so characteristics of your ConnectX 7 network device. So it has 370 million messages per second. It can reach in terms of in terms of computational capabilities, Bluefield 3 has up to 16 ARM cores. I think they're A78s, if I remember correctly. Its computational capabilities are considerably better than those of Bluefield 2, its predecessor. Memory bandwidth on this device is also increased quite a bit. So 80 gigabytes per second is more than the network bandwidth. So you can actually you can actually reach line rate from data that's residing on the DPU, leaving the DPU, whereas in Bluefield 2 you couldn't. The 17 gigabytes per second was less than the network maximum, and there's some other features here related more to storage. One of the capabilities that exists in Bluefield 3 that makes things very attractive in terms of using it as a network accelerator are these memory keys, the alias memory keys. And what that means in practice is you can have since both the host and the HCA or use the same are using the same ConnectX core. That ConnectX core can move data. If you activate the ConnectX core, if you create a few pairs that live on the CPU, it can move data on behalf of memory that's host resident. That is, to be able for the DPU to be able to move data, it doesn't have to move data first to its memory, and then beyond that, it's a very good. It can act as an orchestrator. Actually, probably one of its best. From my perspective, one of its best capabilities. And so, you can do any operation that you can do with network queues from the host. You can also execute from the DPU, and you can do this asynchronously. So you can really be computing on the host and in the background doing other network activity in parallel. The only interference is really the interference that happens because when you read or write to the data that's host resident, you're consuming memory bandwidth there, but the rest there's no. That's a very strong capability there. So we have another capability that exists actually as part of the ConnectX core itself. They're called not data processing units, but data processing accelerators. And what those are ARM5, RISC-V cores that sit in the ConnectX core that can be user programmable. There's a feature that we haven't published much. We're just internally starting to use it. These are cores that run again asynchronous with respect to the main host. But they can be used again for orchestration. So they're limited in terms of what the cores themselves can do. So they don't do floating point operations, for example. But if you're trying to orchestrate things, network activity, and not trying to do computation on them, you don't care about that. Probably you don't need floating point capabilities at all. Of course, they're limited in terms of space. This is stuff that sits in the core itself. The advantage that this has relative to either the DPU or the host itself is that those cores since they sit in the core, to be able to do something with them, you don't have to go across some sort of bus, whether it's a PCI bus or some other thing. So you have the opportunity to post messages at a fairly high rate. So current devices have 16 of these cores. Each of them can support up to 16 threads, and so it's a device that we're starting to try and use right now. But I just want to throw that in so that people are aware of that capability. There are some characteristics here in terms of capacity for various caches, memory, like. We're just starting to look at using it. So we're hoping to be able to use some of the algorithms that we've used very well with the DPU. We use them on the DPA. So a few things to take into account, at least that we think about when we try to use these sort of asynchronous agents or these accelerators for accelerating communication. To sort of our thoughts about how some of the things that need to be taken into account. So from my perspective, the biggest advantage of these sort of units are that they're asynchronous. You know, there's always been, I can remember back, I shouldn't say this, back in the 90s, thinking, how can I get computation and communication to go simultaneously? You really wanted to hide these sort of things. And we couldn't because there was no hardware support for it. Everything was done from the host, and you had to either have the kernel interrupt you or something like that. It just was, there wasn't really an effective way in large HPC systems, in commodity type systems, well, in HPC systems to do truly asynchronous communication. So while there were APIs to support this, there was no hardware level capability to support this. This really gives us that capability. We really do have independent processes that can do that. You know, people can say you have the same thing with additional cores. You know, you can set aside cores for that you use for computation and cores that you use for other asynchronous activities. That's true, but again, there's this mismatch in terms of you're using a very expensive core to do something you could do with a much weaker core, and let the application really benefit from those capabilities. The other thing that's important to recognize is even though you have the ability to compute, you want to have this be a general purpose tool, not a demo unit where you do something that works under very, very restricted circumstances. You got to recognize the fact that there are limitations on what you can do. And so if you put too much work on the DPU, you're going to slow down the application because the application is waiting because the DPU is taking so much time to do its work. So these, at least with respect to BlueField 3, there are a lot less BlueField 3 cores than there are in a traditional CPU. There are also a lot smaller memory bandwidth. Computational capabilities are reduced, and so you really need to take those into account when you do these things. There are acceleration engines, but honestly, the acceleration engines that sit in BlueField 3 aren't really aimed at HPC. They're aimed, or AI. They're aimed at other things. The other thing is it has a very close access to the network. So it also yeah, I mentioned this special memory key. We call it cross-Davami memory key here. It's probably a better term is an alias memory key. And there's some additional optimized data paths between the host and the DPU. So if you need, you can use those for orchestrate or for coordination between the two, between this host and the DPU, without interfering with available memory bandwidth to the network. Another thing that's really nice is the memory bandwidth that the DPU uses for whatever activities it is using for its internal activities does not interfere, does not consume memory bandwidth on the host side. So you can go ahead and run your progress engines or whatever you're running on the DPU without being afraid of causing cache conflicts or the like for the running application on the host. And the other point here too is, even though it's weaker, as long as you can maximize your use of the network, you don't have to do any better than that. The fact that you know, in principle from the host, you could run 10 times the amount of memory bandwidth that you have that the network is capable is irrelevant here, right? You just need enough to, for example, with bandwidth to saturate the network. So from an implementation perspective, all the implementation experiments that we have done are in the context of OpenMPI. The collective operations we implemented in a library called UCC, an open source library. We developed the concept of service processes. These are processes that run on the DPU that service the MPI application. So they're sort of the surrogate of the MPI process on the host. And there's typically a given service process will service multiple application processes, which is actually sort of an advantage because you get a bit of global context about the application, at least from a communication perspective, that you don't have in your traditional one process, one MPI process, one MPI management process. We also developed a library to help us with various miscellaneous things that need to be done to run asynchronously. I won't delve into that now. As a company, we actually have a library now that does at least some of these functions called DOCA. We use UCX to actually process most of the data. No reason not to. There's a lot of optimization in there. So from the outputting perspective, typically most MPI implementation, I'm talking about MPI here, there's nothing unique to MPI. MPI is just the context that we did this work in. Typically, UCC lives within the context of a single MPI process. So in most MPIs, that means also within a single OS process. But in the DPU offload model, we sort of extend the concept of the UCC portion of the communication library to run both in the on the host side as well as on the DPU side. So there's coordination that has to happen between the two. Here's a cartoon of how things look from a process layout perspective. We have job startup, just like any other job, starts underneath with some sort of job system, with some sort of resource manager. We actually modified Slurm so would be aware of the DPU. So it could schedule, co-schedule CPU and DPU resources. There are some number of MPI tasks run on each host, and some different number of service processes that serve these MPI processes run on the DPUs. And from a communication perspective, there can be communication between any of these processes. Communication not just for control purposes, but sometimes even for actually implementing algorithms like the aggregation algorithm. So you can a bit about algorithms. So as I said, what we implemented, what we started out to do in this particular project was to develop optimized collective operations. The goal of these collective operations is really to accelerate applications, not just to show that we could existing applications, actually not just to show that we could take a non-blocking operation and make it run into asynchronously relative to the running application. And so our target from the first place was to optimize both blocking. Actually, blocking was the most important set of collectives to optimize, as well as non-blocking operations. The reason is simple. Most applications today still only use blocking collectives. And so if this is a relevant technology, it really needs to address existing applications. And so what that means is that we didn't take the same algorithms that we run on today on host-only systems, which means 99.9999, however nines you want to put there, on systems today. We had to think of ways that we could leverage some of these asynchronous network capabilities, even with blocking collective operations. So that meant that we needed to think about different ways to do the same high-level data transfer type of operations. And we also did not take this one strategy for both blocking and non-blocking operations. So for blocking operations, the goal is really to reduce latency, the least amount of latency possible. And that means from an algorithmic perspective, the algorithm itself it's actually split between parts of it still ran on the host and parts of it still were running on the DPU. It really depends on what part of the problem you're trying to solve. There are things that you can do on the DPU that you can't do on the host. The other thing too is and then for non-blocking operations, the goal is really to maximize overlap. So the two sort of conflict with each other because if you want low latency, you spread the work based on characteristics. If you want to overlap, your main goal is to make sure that you can always progress communication. So you have to transfer more things down to the DPU so it can progress things asynchronously. So so I'll talk now about two collective operations that we implemented. These are not the only ones we did. The reason, so as I said, most of this presentation are slides that I took from an ASE paper presentation. And in that paper, the goal at the end was to show the impact on two real-world applications. And so this is why we selected these collectively. So the first one that we worked on was the MPI Alt-Al-V, non-blocking Alt-Al-V operation. And so from a high level perspective, so this is for large data, by the way. I'm sorry, it's not for small data, but for large data. So in large data operations, the main goal, one of the main algorithms that are used is what's known as the ring algorithm. So it's used in a variety of different contexts with different implementations, but the ring algorithm is basically a way to sort of let processes keep their endpoints separated while they're doing the data exchange, hoping that loose coordination is sufficient. And so that's just an algorithm that's frequently used. So conceptually, one of the ways to implement it, very simplistically, is the first step you'll do something with a process that's one ahead of you and with the one behind you. So if you're doing an Alt-to-Al-V, it would send data to the one process ahead of you, wait for data from one process behind you. When those two are completed, you go to +2, -2, etc. That's for Alt-to-Al-V. That's the sort of algorithm that you would use, the sort of ring algorithm, a very simplistic ring algorithm that you would use. So what we did, the main modification that we made to this algorithm, so the biggest issue with a ring algorithm is when you're waiting on a set number of processes of things to happen before you go to the next step, is if you have load imbalance in your application, which is close to 100% of the time, that process, one process may be waiting for a long time for data. There may be one process that's very late, and at a minimum, if you have just one process that's late, you're immediately blocking half of the data that needs to be transferred in the whole operation. So the most important thing to try and do here is get around that limitation. It's rather simple to do. We modified the algorithm a bit so we don't block in those sort of scenarios, so we can continue and progress communication and not be blocked there. You can't do that if you're in an environment. Well, you can, but it's rather expensive. But if in your environment where the CPU, you're using the same CPU for both computation and communication, that's just not really feasible. We use service processes basically on the DPU to manage the data exchange. For large data, we just let the DPU handle all the data exchange. For small data, you don't want to do that because of latency implications. And so the DPU itself will manage all that ring algorithm, and when it's done, it notifies the host that it's done, and the host can notify MPI that it's done, which notifies the host the application, and so on. The other algorithm that we talk about and we are presenting here is a blocking All-Gather-V. But again, it's very similar in nature to what we did for the non-blocking Alt-Al-V algorithm the non-blocking alt-to-all-V algorithm, except that we also do an optimization that's been reported multiple times in the literature. Is we take care to deliver data from one process to a single host only once. We don't deliver the same data to multiple processes on the remote host. So we have some ways with the DPU to help us even with that distribution. Include work sharing. So we sort of have a pseudostatic allocation of work to these shepherd processes, to these service processes on the DPU. But when that becomes when that blocks the operation, we just move on. We just pass that work to another one of the service processes. And the reason it could block that operation, because if the DPU only knows about activity on the host once the host is told that the collected has started. So if one process starts before the other process does, it has nothing to do with that notification. So that's why we let the notification be passed. So a bit about performance. So the first thing, this is just a generic slide about the actual network performance capabilities of the DPU on Bluefield 3 versus the ConnectX core. The characteristics themselves, the details themselves aren't so important. So the bottom two curves in both cases show the performance with Bluefield 3. Whether it's latency for a ping pong operation or bandwidth, or for bandwidth test. Blue is the host, ConnectX 7. Yellow is Bluefield 3. We can see that both of them have basically the same, very similar performance characteristics. That's the key take from here. This was not the case in Bluefield 2, so it's only addressed in Bluefield 3. Another thing here, so we talked about having service processes living on the DPU and serving multiple MPI processes on the host. So one process typically serves more than one. The question is, how far can we carry this and still get performance benefits? Right? If you have to have one service process service one MPI process on the host, if you have more MPI processes and service processes, it's a loss, right? You're not going to benefit from that. So the main takeaway here, this is a latency of larger message sizes. These were the message sizes that were relevant to the applications we were working on. The main takeaway is if we used one service process, the mapping to 32 MPI processes gives some level of performance. That's the first green curve on the left. But as soon as you double it to two service processes, that is one service process serving 16 MPI processes, you gain most of the performance benefit using these service processes. So you don't need to use a lot of service processes to gain this performance advantage. And again, this is with weak processes. That's both for the altogether V as well as the I-all-to-all-V. Yeah, you improve a bit as you increase the number of service processes, but you've gotten most of the benefit early on. The other thing here, so this is just your standard. This is how the implementation of the DPU compares to other implementations, OpenMPI, standard OpenMPI, as well as some of the optimized versions. And the key takeaway here, if you look at all the details, you get lost in it. But the key takeaway here is that the performance. This is again latency for the all-gather V. The latency of the offloaded operation itself. This is This is latency measured in an OSU test where you loop in a tight loop around these operations. Latency is similar to whether or not you use the DPU. Just what I would have expected. Okay, so we're not seeing, in terms of those very simple, rather well load balanced tests, we're not seeing large improvements or any improvements, as a matter of fact, in terms of performance. You see some latencies are a lot higher there. those are deficiencies in the implementation. Basically, they're not paying attention to some detail that they should. So they're not characteristic of the capability to use an asynchronous device. Here. Oh, somehow the slide got inserted by accident. This is just a graph of scalability of latency for all gathered V as a function of number of processes. You would expect it to scale linearly, but in papers like this is what people expect to see. So this is exactly the sort of behavior that you would expect. If you look closely, actually, if I remember correctly, the DPU performs quite a bit better than some of the CPU versions. But again, those are most likely bad choices in terms of algorithm on the host side, and not so much anything that's intrinsic in the implementation itself. Overlap capabilities. So if you have purple is the offloaded version. The blue ones are using non-offloaded implementations, and as you would expect, if the host is busy, it can't progress communication. This is well known. This just shows that the design does what it was intended to do, even the messages as small as 16 bytes. Again, for all to all V, high all to all V, a similar graph on performance in terms of for a fixed size, how performance varies with number of processes. It's a behavior that one would expect. But now we get to applications. This is for things to get a lot more. This is where you see the benefit of rethinking algorithms. This is an FFT, actually FFT library. What it does, for those of you that are familiar with it, it's P3D FFT. What we have here is running the Fourier transform on 4 variables in a variety of configurations. So four hosts, 32 processes, 8 hosts, 32 processes, with 32 hosts and 32 processes, using the offloaded version, which is in yellow, and then both host-based blocking, non-blocking algorithms, as well as blocking algorithms. And the numbers in red here represent the change in performance, the improvement in performance relative to the DPU offloaded version, which is in yellow. And so you can see, depending on what sort of comparison you try and do, you get anywhere from 14% improvement in latency up to 49% improvement. So this is really where we start to see the benefits of using being able to run things asynchronous and changing the algorithms that we use. So we tried to understand a bit why this was happening. And so for the IAL V, it's not too hard to understand here. If you look at the times, this is data from 16 node case and the 32 node case. We see, first of all, the time spent in IAL V goes down. This is what you would expect, right? Because it's able to, computation can go on, you're overlapping computation, communication. WaitIO reflects the completion time, so it also reflects time for the non-blocking operation, and operations, and these also go down quite a bit. And those seem to be as you would expect, the main reasons you would get performance improvements here because of this overlap. But when we go to looking at the characteristics of blocking algorithm, for this we used Octopus. Octopus is a VFT material science code from the Monks Block Institute in Germany. The reason we actually got into this was an RFP. This is one of the codes that was relevant, and so we had the challenge of trying to optimize the code for the collectives, the all V for it. And what we have here is the overall wall clock time to run the application. 3 different scenarios. One with the offloaded version, that's the light blue time for run the code. I use green is stock open in PI, and purple is the NVIDIA's optimized version of OpenCX. Notice that the base here is 300 seconds, which is about half the total number of runtime. So it's not. So the actual improvement in performance using the offloaded version of the non-blocking collective is about 25%, and it's not factor 2. But there is substantial improvement. Oh shoot, I took away one slide that I was hoping to show. So we, in this particular case, we actually analyzed, like we did before, we looked a bit at how the time distribution changes. And we certainly did see a reduction in time spent in Gather B, which is what we would expect or we would hope for. We also saw some other improvement in other collectives that we didn't change at all. We thought it had to do perhaps with the offloaded version maybe somehow because things complete faster. The application gets a bit more in sync quickly. That's not what we saw when we looked specifically at that in the application. So at this stage, we really don't understand this, and this is one of the things that we want to understand. But we're still a bit, not more than a bit, we're still a little puzzled as to why other things seem to improve. So it would be nice to understand it so we can understand the implications for the broader implications for these sort of changes. So back to the second slide I showed before. Here a few more applications. There's actually the weather code at the bottom right is the GSAM code from JMA. So we saw about 6% improvement in its runtime when we took advantage of the ability to overlap computation and communication. The one on the top right hand is actually the UK Met Office analysis code. It also improved, and I have the other two here. So these weren't selected as these weren't four of many. These were four that were very relevant to active RFPs. We wanted to improve their performance, and so that's why these are selected. Of course, there are applications that don't use these collectives. Of course, they wouldn't benefit from these. Oh, I do have it. Put it in the wrong place. Sorry. That's it.
Thank you very much. So any questions or comments? Thank you very much. Thank you. Okay, so I would like to introduce next speaker briefly. Takeshi Nani from Kyushu University. So we have 4 Takeshis in the Japanese HPCN. So he's one of them. And he's associate professor from the Research Institute for Information Technology and the Department of Information Science and Technology from Kyushu University. So his major research topic is the runtime systems of power computers. And his team has been developing a technology for dynamic optimization of runtime systems. He's now leading he's a leading PI of the JHPCN international project, a study on the real effect of non-blocking communication started this April. Actually, so all of the speakers today, the 4 speakers are members of this project. And I expect that he will briefly describe this project. So please join me to welcome.
A very high introduction. Okay, so thank you. So I'm Takeshi Nari, and today I'll talk about this topic and studied on the real effect of non-blocking collectives. So this talk is about overlapping communications before DPUs. So we don't have a overlap between me and Rich. Okay, so first, I'd like to talk about what is non-blocking correctives and the motivation of our study. As you know, the corrective communications are very important communication. It's typically used in many physical or scientific applications. And the problem is it consumes time and mainly, usually the time for corrective communication increases as the number of processes increase. With non-blocking correctives, we expect that we can overlap such communication with other computation so that it can hide the time for corrective communication and achieve higher strong scalability. That is expectation. And the reality of NVC is there are mainly two requirements. One is requirement for implementation of communication libraries. So to overlap communication with computation, they need some mechanisms to progress corrective communication in the algorithms for corrective communication in parallel with computation. Of course, the effect of overlapping so communication hiding depends heavily on the progress, the progress mechanism. And another requirement is requirement for application. And programmers need to modify algorithms so that it can overlap communication with computation. So programmers need to modify, but without sufficient knowledge about how the effect of the overlapping will be, it takes courage to modify their programs. So we started this study, and there are other approaches to overlap communication with computation, and what we call it is non-blocking corrective approach. So it holds blocking correctives from one of the threads in a process, like this. So, for example, each process runs eight threads, but we can let one of those 8 threads to call communicate blocking correctives like this, and after that do some computation, and while other threads perform computation. In this way, communication and computation can be overlapped, and if the computer load can be balanced carefully, then maybe the program can achieve the sufficient strong scalability. And we expect that NBC can realize this kind of effect or better result, better effects with less programming effort. So we expect that we don't have to care about load balancing among threads. So we started the JHPCN project. Let me talk about this project. JHPCN is a kind of program that supports research for the usage of computer resources in Japan. And in our study, we are investigating the effect of non-blocking correctives with 3 topics. First one, we studied the availability and how to use the NVC non-blocking correctives on JHPCN supercomputers. So supercomputers provided by JHPCN. And topic 2 is to perform benchmarks and build performance models of overlapping by non-blocking collectives. And topic 3 is about the effects of overlapping by NVC in real applications. So in this talk, because of the time, I limited my talk for these two, topic 1 and topic 2. And we are using some academic supercomputers provided by this program. So these are the members of JHPCN, so many. There are 35 members from all over the world. As for topic 1, we have members from the academic supercomputer centers in Japan, as well as the members from NVIDIA, and also some members from the Ohio State University that they are developing their own MPI libraries in pitch, and also the Ohio micro benchmarks for benchmarking. And most of those topic 1 members work for topic 2, benchmarking and performance modeling. And as for topic 3, the applications, we have many members from Japan, as well as the United States and Japan. And these are the machines we are using in this project. In total, we have 8 supercomputers. They are, as you see here, they are all academic supercomputers, but they are available for industry users also. And 2 of the 8 machines uses TOFU as the interconnect, and other 6 supercomputers use different versions of InfiniBand. And as for the progress methods for non-blocking collectives, so as I told, non-blocking collectives require some mechanisms to progress the algorithms of collective communications in parallel with computation. So please assume that these are the algorithms of collective communications. Usually, such algorithms consist of these kinds of communications, weights, and some computations. So non-blocking collectives need some mechanism to progress this algorithm in order. So usually the MPI libraries make some progress on these non-blocking collective algorithms when one MPI function is called. So the programmers of the applications can force progress of such algorithms by adding MPI test function appropriately in their applications. And these two are the mechanisms that progresses without modifying their program, modifying the application. One is offload to external devices. So as mentioned in the Rich's talk, some of the collective communications can be uploaded to DPUs briefly, or in some of them can be uploaded to the switch, and that technique is called SHARP. And also, Fujitsu TOF has its own mechanism for progressing. It's called TOF barrier. And another one is using threads. So using a progress thread. And so in this mechanism, at the beginning of MPI program, each process invokes one additional thread so that it can offload the processing of collective communication on that thread, while the main threads perform the computation. And the availability of these progress threads depends on the implementation of MPI library. And so far, we have confirmed that these three MPI libraries have options to enable this progress thread mechanism. And as you can imagine, adding one extra thread consumes some extra CPU resource. And so that can affect the total performance of the application. But with Fugaku and its compatible machines, you can the machine can run these progress threads on the dedicated special core called assistant core, and this avoids the consumption of CPU resources for the main computation. So we have studied the availability of the progressing mechanisms, and so for Sharp, we expected that all InfiniBand connected supercomputers can use Sharp for number of scheme collectives, but so far we have confirmed two, Tsubame 4 in Tokyo Institute of Science Tokyo. and another one is Genkai in Kyushu University. And as for progress threads, we confirmed that most of the InfiniBand connected computers can enable progress thread. And this alpha S, this is a vector processor machine. So its MPI library is a little bit different from the ordinary open source one. So we need to check its availability. And for the top connected supercomputers, we can use TOF barrier and also assistant core. And today I will talk about this Sharp and progress thread. Okay, so we examined some MPI libraries and options, how to enable Sharp for overlapping. And so far we found that HPCX, that is provided by NVIDIA, and it's based on OpenAPI. 2.17.1, this version can enable the overlapping with Sharp, and it is based on OpenAPI 4.17. And there are two methods to enable Sharp for NVC. One is using UCC, Unified Collective Communication. This is introduced by Rich in the previous talk. This is open source collective communication library. And another one is NVC with HCore. HCore is a collective communication library developed by NVIDIA. And so we can specify these options to enable non-blocking collectives with sharp, with UCC with these options, or H-core with these options. And at this point, we couldn't find other MPI libraries or other HPCX versions that can sufficiently overlap non-blocking collectives with sharp. Maybe there can be, but we continue searching for other methods. Okay, and next one is progress thread. And we found, so far we found that MVP 3.0 and also Intel MPI 2021.12. These two can enable progress threads with these options, these environmental variables at runtime. And at this point, maybe I'm missing some documents or manuals, but I couldn't find which option can enable progress threads in OpenMPI or HPCX. So we measured the effect of overlapping, so overlap ratio by non-blocking collectives by using OSU micro benchmarks, and for these three non-blocking collectives, all reduce, all gather, and all to all. I used Genkai in our university, Kyushu University. And I examined NBC mechanisms, sharp and progress threads. And I used 128 nodes to measure. Okay, so this is a result of all reduce with one process per node. So in total, it's 128 processes. And x-axis is a size, message size, and y-axis is the overlap ratio from 0% to 100%. So 100% means all of the communication time could be hidden by the computation. And blue line shows the results with Intel MPI, green line shows MPIC, and red line shows the HPCX. And so first, let's see the effect with sharp. So this line and this line, these are the overlap ratio with HPCX. And this curve, and this line is HPCX with UCC plus sharp. And this one is HPCX with H-core plus sharp. So open source UCC library or the NVIDIA's H-core library. Okay, so both of these mechanisms can overlap some communication time for all reduce. And H-core and the overlap ratio of H-core drops down to 0 after when the message size is larger than 16 kilobytes. So maybe there is a kind of limitation in the H-core about the message size for using sharp. And maybe we could change some threshold by some other parameters. By default, the result shown that H-core can show the overlap ratio until 16 kilobytes. And for other choices of sharp, like pitch or Intel, they didn't show the sufficient overlap ratio. So this is pitch, and around these Intel. So they couldn't overlap. And when we increase the number of processes to 2 per node, 2 processes, I'm sorry. Let me show the results about the progress rate with only the same one process per node. So this green one shows progress rate overlap ratio with pitch. And this blue one, this one shows the Intel MPI with progress rate. These two shows sufficient high overlap ratio. There is some irregular measurement. I'm not sure what is happening here, but mostly they show the high overlap ratio with progress rates. Okay. So when we increase the number of processes per node, the overlap ratio with sharp drops down like this. So this line is the UCC plus sharp, and this line shows H core plus sharp. So H core plus sharp shows some overlap, but UCC plus sharp doesn't show sufficient overlap ratio. And pitch still showed a high overlap ratio with 2 or more processes per node. And for Intel, when we use progress set with 2 or more processes per node, it caused some error. So we couldn't measure the result, measure the effect. And these are the results with all reduce. And this is the chart with altogether. And for altogether, of course, we can't use sharp for altogether. So we compared with or without progress rate. And again, the progress rate could be used only with empathy. With Intel, even with 1 process per node, it caused error with progress rate. So we could measure this pitch result only, but it showed sufficient overlap ratio. And when the number of processes increases, the ratio is high. And this one shows all-to-all results. And the results was similar to altogether until 256 bytes. But after that, the pitch causes some error. I don't know what the problem. Maybe it is a problem with library, or maybe it's a problem in the benchmark program. So we are now investigating the reason. And this is 2 processes per node. The situation is almost the same. So so far we got these results. So with sharp, we could overlap or reduce with HPCX plus UCC plus sharp, or HPCX plus H-core plus sharp. And so the effect depends on the number of processes per node. And as for progress rate, we could rely on pitch only for now to see the sufficient overlap ratio. But even with pitch, we need some more study how to deal with larger message sizes with all-to-all. Okay, so far I showed some results with sharp and progress rates. So the interest there can be some interest about which one is better, sharp or progress thread. But it's difficult to compare these two mechanisms because the overlap ratio measured by OS micro benchmark is not suitable for comparing different NVC mechanisms. And the reason is to measure the maximum overlap ratio in this OS micro benchmarks, the computational amount is automatically adjusted according to the communication time. So it first measures the communication time in the beginning of the benchmark and start the non-blocking corrective here. Then repeat computation until it reaches to the communication time. So the amount of computation is adjusted at here according to the communication time measured in the beginning. So the amount of computation differs on each measurement. And so the amount of computation can change with different mechanisms. So it's difficult to do pair comparison among different mechanisms. Also, the computation in the benchmark is as shown here. It's not much threaded. So as I told, the progress thread consumes some CPU resources. So it affects some effect to the speed of computation if it is multi-thread application. So we need to do some. We need to consider such effect by progress thread. So unfortunately, OS micro benchmark is not sufficient to do so. So we are now building a new benchmark program to compare different NVC mechanisms. So we fix the compute amount and overlap communications with that fixed amount of computation, and so that we can fairly compare the mechanisms. And also we use multi-threaded code for computation to see the effect of by the progress thread. And after that, we are going to build a performance model with communication and computation overlap, how the effect will be. So that the programmers can determine if they should modify their codes to overlap or not. And also in topic 3, the members of our project will apply NVC on their application. Okay, this is the end of my talk. Thank you very much.
Okay, thank you very much.
Thank you.
Okay, so according to the schedule, we have about 15-minute break. But so actually, so we need to leave here 4:30 because we have another meeting here from 5 o'clock. So therefore, so let's have a 5-minute break. So start from the 3:35. Okay, so let's start the second part. And so next speaker is myself. It's a little bit different aspect for focusing on the application. The title is "The Road to AI for Science: Exploring Software Sustainability Through Apply." Actually, so this talk is based on my talk, which was held in the East Time 24, which was in Osaka, mid-September. So This talk was held in this sustainable project for HPC software and application workshop hosted by Dr. Elaine Rayburn from Sandia National Laboratory, who is doing the software sustainability. So this talk is based on the talk. So these are the list of the courses. Shinji is the next speaker, and Takashi and Hisashi. So they are the especially couplers and climate station. So I'd like to thank my sponsors. Okay, so what is the coupler? Okay. So in this talk, I focus on coupler. And coupler is originally a tool for coupling multiple scientific applications loosely. So you heard about the multi-physics coupler, such as the ocean atmosphere, fluid structure. So this is a very typical case. And scientific applications include a lot of procedures, such as mesh generation, main solver, visualization, etc. So coupler mainly couples the multiple main solver. Okay? And the complex workflows that combine scientific simulations, data simulations, and analytics, and the machine learning have become very common. So we call this integration of S plus D plus L, so taking initials for the simulation data and learning. Overall time to solution is an important issue from the viewpoint of the performance, while optimization of each procedure is also essential. So in my projects, coupler has been extended to a tool for efficient workflow in recent 10 years. So I try to show the pathways towards sustainability through this history of coupler. So this is my history of the project and budget starting about 2011. Mainly we have 3 big projects. So because this one is very small, and these are the budget based on the Japanese yen. So actually, so Japanese currency was so against the US dollar is changing. Now it's 150 or something. But so in these days, it's almost 100. But anyway, so you can estimate the scale of the budget. Okay, so I'll talk about the 3 projects. And this is the history of our supercomputers in University of Tokyo. So we have nearly 3,000 users. And so more than 55% are outside of the University of Tokyo. And we have some international users and also industry. And recently, we have more systems with the accelerators, so these printers, such as that. Okay, so I'd like to talk about the first project, the PP of HPC, so supported by Japanese government. And the corresponding supercomputers in our center is one is the Oak Leaf effect. It's a commercial version of the K computer. Okay? And another one is the Oak Press Pack. It's our Xeon 5 system. So under collaboration with the University of Tokyo, we can see it's a very big system. So this is a very brief overview of the PP of HPC. It's an application framework with an automatic tuning. So this was originally a 5-year project supported by JHT Crest. It's a governmental funding. So PI is myself. And but finally, so it was extended to 2018, 8-year project under collaborations with a German project, that's SPPXA. So it's a very big project, a team with 7 institutes, more than 50 people, and 5 postdocs from various types of fields. And we still have a website and also app. So if you are interested in, so you can download several software. So all things are in the English documents and the MIT license. So our main purpose was developing framework for developing the software framework for the various types of the discretization, such as finite element, finite size, And so including several layers of the software. So this is a featured development. So one new thing is automatic tuning language, and another one the H matrix library, and also we developed a lot of sparse linear solver. But one of the very significant developments as a PP OpenMath MP. MP stands for the multi-physics. It's a coupler for multi-physics simulation. So yeah, this is one of the very big developments. So this is a very brief overview of the PP OpenMath MP multi-physics coupler. It's a weak coupling tools. Each application does a single computation, such as ocean atmosphere and fluids. So this was originally developed as a coupler for NICAM and COCO. NICAM is the atmosphere with the unstructured mesh, and the COCO is the ocean simulator with the structured mesh. So in global climate simulations using a computer. And one of the features is a non-centralized and fully distributed operations, and there are no master processes. So this is very common now, but 10 or 15 years ago, so it's a very new idea, and it's a very scalable, nice coupler. And the developed coupler is extended to more generally. So this is one of the results using this coupler. Solving the mechanism for the super El Nino phenomena in late previous century. Okay? So we use the K computers, and they provide a very nice data. So this is one of the articles of the newspaper at that time, and they say we have some new scientific finding using K computer, but there are no statements about the coupler. So because it's not so common. And we also extended this coupler to the coupling for the seismic simulations for very wide range wave propagation and building values. So this wave propagation part is by finite difference, and this building vibration part finite element. But I don't get into the details, but so we apply our coupler to connecting two types of the big applications, which are developed in our project. And so we apply this coupled simulation to the earthquake simulation in Kobe area. And so this is a result. And actually, so this is a building of the K computer. Now Fugaku is inside. And we have a wave propagation for the wide range of the place. And so this is a very detailed model that we can. And we use up to the more than 4,000 nodes of the FX10. FX10 is a commercial version of the K computer. So this is a result of the first project. Okay. So next one is the H3 OpenVDX on WaitIO V1. So it's like this, and so this project just finished this last month. Okay. So it overlaps with the last part of the OpenPress pack, like the Xeon 5 system, and also some overlap with the WaitIO V1 in the first floor. And integration of the simulation data and learning, so we call this S plus D plus L, has been our main strategy in recent 10 years. So we have various types of workloads, so in addition to the very traditional simulations for the computer science and engineering. We have a new users and new workloads. So in the area of the big data analytics, AI, machine learning. And the integration of the simulation data and learning is very important towards the society 5.0. The human-centered society proposed by the Japanese government by integration of the cyberspace and the physical space. So BDEC, big data and extreme computing, is our so name of the project. It means a platform for integration of S plus C percent. But in our case, we are focusing on the simulation part. And the data and learning are so supporting the sophisticated simulation. So this is the idea of the AI for HPC and so classical AI for finance. So we still BDEX drone on the first round with this building is the first BDEX system started its operation 3 years ago in May, okay, by Fujitsu. And we have a totally 33 petaflops peak performance, and the memory bandwidth 8.38 petabytes. We have two types of the node groups. So why the simulation node groups are called Odyssey? It's based on the Fujitsu's prime HPC effect 1000 based on the ASE effect, with the commercial version of the Fugaku. So totally, we have nearly 8,000 nodes, and the size is 1/20 of the Fugaku. But we still have a peak performance of the 26 petaflops. So another part is the data learning node group, Aquarius. It's for the data analytics and AI machine learning workload. So it consists of the Intel Xeon Ice Lake and the NVIDIA A100 Tensor Core. So totally, we have a 360 A100. And the nodes of this Aquarius part are connected to the external resources directly. So we can get the observational data, something like that, for the outside resources. Okay? So this is how we utilize this system. So we have a simulation nodes and the data analytics node. And so, as you know, real world simulations are non-linear, and we need a lot of parameter studies. And in order to optimize the models and parameters, we utilize data analytics and machine learning. So we can accelerate the cycles for the kind of non-linear simulations. So this is our final target. Okay, so this is a research area based on the machine hours for the last fiscal year. And we have a two general purpose CPU systems. So this one is a Vitaya, and this one is a Odyssey, and this is Aquarius. So earth science, engineering, material science, and energy analysis. So they are the very typical area of usage, the very classical computer science and engineering. But in the case of the GPU, we still have a lot of users from the CSE, but we have a lot of usage for the AI. So mainly it's for the experiments for the large language model. And the bioinformatics includes genome analysis and medical image recognition by machine learning. So, the new area of research. We also develop a software. So this is another funding for research. And this was a 5-year project supported by the Japanese government from 2019 to the end of March of this year. Okay? And the leading PI is myself, and the total budget is roughly half compared to the previous year. So these are the main members, which cover the wide range of expertise: computer science, computational science, numerical algorithms, data science, and machine learning. So you can see the wide range of the research area and the institute. So we have 3 innovations, and but here we are focusing on the software and utilities for the heterogeneous environment, such as the Wisteria. So Kafra is included in this third category of innovation. So actually, Wisteria BDX01 is the first really heterogeneous system in the world. And you can see, so we have a different architecture for the simulation node groups and so this data analysis. So in order to combine these two parts, Odyssey and Aquarius, single MPI job over so Odyssey Aquarius is impossible. But fortunately, so these two parts are connected through the InfiniBand EDR with so 2 terabyte per second, very rich memory network bandwidth. So we developed a new software called H3 OpenSys WaitIO socket. So it's a library for interprocess communication through InfiniBand EDR with MPI. So this is the examples for the API for the WaitIO library. And this was developed by Shinji. And so Shinji will talk about the details next. Okay. And instead of calling, for example, MPI ISEN, we can just call WaitIO ISEN. And so we can easily call the different architecture. Okay, so we also extended this coupler, and so we have two types of the new features. One is the coupling of the simulations on Odyssey and AI on Aquaria. Okay. So as I mentioned initially, so this coupler was developed for the MPI-based environment. But so by combining with the WaitIO library, which I mentioned in the previous part, we can do this type of the coupling on the heterogeneous architecture. Okay? Odyssey is suitable for the simulations, and Aquarius is good for the machine learning type of workload. So we can combine the two workloads. Okay, so I will briefly overview several applications where we use VCR VDEC 01 and HP Open VDEC software. So one is the 3D earthquake simulation with a real-time data observation and assimilation. And as you know, so we have a lot of earthquakes in Japan. And so our motivation is trying to do the accurate so strong motion simulation so by utilizing the observational data. So basically, so what we are doing is so collecting the results of the earthquake simulation by the observational data real time. Then we switch to the pure data. So this is a system which we constructed on our supercomputer. And this green part is observed data from outside. And Aquarius is getting the data from outside. And they are doing the filtering. Okay? And the filtered data are sent to the Odyssey part. And this part is doing the simulation and data archiving. And finally, the visualization is done by the GPU part. So this page shows a sample of the code so for the communication using the WaitIO socket. Okay? And so this sending part is so these are total code and call WaitIO API I send so code here. And so this part is the receiving part and call WaitIO API I receive. So in this way, we can easily do the communication between the totally different architecture. So, okay. So this is one of the results for the of Niigata 2007 earthquake. This is a very big earthquake. So we can do type of communication. So another example is the global cloud simulations plus AI coupling. Okay. And this is so based on the coupling of the simulations on Odyssey and AI on Aquaria. So, okay, I skip the details. Okay. And the last one, okay, I have some slides. And so this is by my colleague, so Yashiro-san and Alpha-san. And in the case of the global atmospheric simulation, so generally we combine with the coarse model, which is for the parameterization. And generally, so 75% is spent for this high resolution model, and 25% is for the coarse model. And our idea is that to replace this part with AI. And we are doing the simulation on Odyssey and the training and inferencing Aquaria. Okay? So using our software, we can do this efficiently. So this part is almost here after training. So last one is the ensemble coupling. And this is utilizing the capability for data assimilation in the Apply. Okay? So we apply the so-called ensemble coupling. So as you may know, if you do the weather prediction, we need an ensemble simulation where we do a lot of parameter studies and doing the estimation. Okay? It's very expensive. Okay? And for example, if you want to solve this global atmospheric simulation with a 14-kilometer mesh, you need a 160 node of Odyssey. Okay? And generally speaking, we need to do the 100 cases for that. And we need a lot of commercial resources. So if you want to do the only 9-hour ensemble data assimilation, we need almost 2,000 node hours. Okay? Actually, it's not so expensive, but so generally speaking, we need more than this, so 2 weeks or 1 month. Okay? So anyway, so 2,000 hours is one number. And I skipped the detail, but we recently we developed a new method called ensemble coupling, where we are utilizing the very coarse model and just one very high resolution model. So by this way, so we are coupling this coarse model and very fine model. So in this case, we apply the meshes with a 224 kilometers, and this one is a 16 times coarser compared to the original mesh. Okay? And finally, we can get a very saving time for the computations. And originally, we needed more than 2,000 hours. Okay? But now it's less than 20 hours. So it's 100 times improvement. So this is one of the results we did in this ensemble coupling. And if you compare the accuracy of the original result using the very high resolution model and the low resolution plus a high resolution model, so you can see there are no. So yeah, it's a very reasonable way, and we are now validating the model using more long time, weeks or more. Okay, so this is the second case, and the third case is a JHPC quantum. And actually, so anything is possible with this WaitIO library. And so it's possible for the WaitIO over the internet or cloud. And also it can connect it to various types of the CPU, GPU, and other devices, such as quantum computers or AI devices. So JHPC quantum started last November, so just 1 year before. And it's a research and development of the quantum HPC hybrid platform for exploring the computable domain. It's a 5-year project supported by Japanese government. RIKEN and SoftBank are the primary companies, and the University of Tokyo and Osaka University are the cooperating over that. So this project has a strong focus on the industrial application. So that's why SoftBank is involved. So in this project, we are introducing 2 real quantum computers. So IBM's the superconducting machine with more than 100 qubits, and another one is the continuum ion trap. Okay? So we have several target applications, but so personally, I'm interested in the quantum machine. Okay? Okay, so this is the history of the project and budget. Okay. So we are using the WaitIO VDEX and the two real quantum systems, which will be introduced next year. So as you know, current quantum system is not so powerful. So therefore, usually we utilize that for the accelerator for the supercomputer at the CPU. So that's why we have the idea for the QC-HPC hybrid environment. So role of the University of Tokyo is the research and development of the system software for the QC-HPC hybrid environment. So this is just an extension of the HP Open VDEX at the previous project. Okay, so actually, we have no quantum computers now, and we are now developing a simulator for the QC-HPC hybrid. And fortunately, Aquarius is something like quantum computer, and Odyssey can be considered as a supercomputer. So now we are constructing the QC-HPC hybrid environment on our WaitIO VDEX server. Okay. And we are now developing the two types of the software. So one is the scheduler, and another one is the communication library based on the Open VDEX in the previous project. Okay. And so this QC-HPC hybrid is possible in April 2026, so less than 2 years from now. And so quantum computers can be accessed from supercomputers in Japan. And the multiple HPCs and QC will be available in 2028. So we are now developing several software and so extension of the WaitIO library. And so I think Shinji will talk about this later in detail. And one is the WaitIO for Pi, so it's a Python interface. So another one is the WaitIO router, it's a communication library among supercomputer centers over time. So this year, we are mainly focusing on simulators on WaitIO VDEX01. And so next year, we extend this idea to the real QC. Okay, so I'd like to summarize my talk about the sustainable coupler. So we start with the MPI-based coupler for the atmosphere and ocean and other types of applications. So next one is the heterogeneous environment combined with the WaitIO. So combined with WaitIO is a very powerful tool for the heterogeneous environment. And we did the integration of the SDL, S plus D plus L, and also ensemble coupling. And the next challenge is the QC hybrid environment. So this is also heterogeneous, but more challenging. And the further development of the WaitIO, such as the WaitIO for Pi and WaitIO for router. So sustainability of the software, such as coupler, strongly depends on continuous funding. I think it's applicable for every type of the software project. And the extension of the target applications and systems with additional development for adaptation, such as the WaitIO, is very important. And the coupler is a very important workflow tool towards the AI for science. So therefore, we need to develop this type of software for a while. Those involved must always keep their eyes open and pay attention to whether it can be applied somewhere. So that's what I have been doing in recent 10 or 15 years. And so we need to do this, so continue to do this for a while. Thank you very much for your attention. So I think, so Shinji will talk about more details on this type of the library. Okay, thank you very much.
Thank you.
So, my name is Shinji Tsumoto from the University of Tokyo. Today, I'm going to talk about center-wide heterogeneous coupling computing with WaitIO. But maybe I talk this time several times, so I slightly change for which. So, here's the outline of my talk. And first, I talk about VSBILIC 1 and H3 of BILIC, but media Professor Nakajima also talk about that. I almost skip about a thing. And then I go to some of the WaitIO overview and its application. And I will talk about some of next way to development at JHPCN contemplate more detail of the WaitIO. So as Professor Nakajima talk about some of the VSBILIC 1. It's some of the world's first real heterogeneous computing system. Because maybe Ken talk about that VSBILIC 1 two kinds of systems. It's both heterogeneous. One is Intel CPU with NVIDIA GPU, and the other one is ARM CPU with also interconnected device. And this combining some Odyssey and Aquarius difficult, so we developed the WaitIO and heterogeneous coupling computing library. We developed not only a conventional library, but also a coupling job scheduler. In this VSBILIC 1 system, these two kinds of different job schedule operated. So, but user only two job submit for Odyssey and Aquarius with special resource definition. And this coupling job schedule automatic look up the backend of the resource, and when both are available, the job started at the same time. So user can easily use the heterogeneous coupling job for the VSBILIC 1. This is almost already talk about the Ken-san also. We developed some HC open BW. So there are three innovations. There's a new principal application and data-driven approach, and there is a system software. So WaitIO is developing this kind of software and utilities for heterogeneous environment. So I talked some of API with WaitIO. WaitIO is originally developed for there are several dedicated heterogeneous MP application. This MP application is coming with MPI is with compiler and Intel MPI. WaitIO on top this kind of a multiple application communicate to multiple heterogeneous cluster. So in this environment, with each MP application has defined parallel, and user can easily combine each parallel block MP application, and user write a program to combine some application using WaitIO. That's only. So user can combine and realizing the coupling application using library. And this is some three kind of job on this case. And in the WaitIO, this is WaitIO some instance. So in this case, user can choose every process in every some implementation and create a group, a WaitIO group. After that, user can communicate in the WaitIO ranks for using some NPM manner. That's in the WaitIO send, WaitIO receive, and wait. That's all. And also some miscellaneous functions such kind of group rank and group size. That also WaitIO com rank and command group. And but currently, WaitIO definition does not know the data type, so it is difficult to translate to some WaitIO to MPI. So we developed the WaitIO MPI conversion library. It's also same as WaitIO MP application, but only adding some WaitIO underscore prefix in some function name, data type, some operation. That's kind. That's easy. Actually, here's a picture 3D real application realism program, but user can change the WaitIO the red part. For example, some definition part, and here's some WaitIO ISEND. It's adding a WaitIO underscore on top of the WaitIO ISEND. And data types in the some precision or something like that. It's easy to translate. And here's performance on WaitIO socket. There's maybe a part of some WaitIO because of socket and POSIX socket and POSIX file and the combined it's hybrid. This is maybe eGAP communication is derived on socket and the random part of the file. In that case, WaitIO what I say in the maybe ASIC4X is not so fast. So socket communication. And here's a communication, some performance. Here's a number of bytes, and here's a megabyte per second. And this is WaitIO socket. This is not so good because only some 200 and 300 megabytes per second because of some limitation with the ASIC4X ARM processor and some IP over TOEFL, there's some very limited resource. So it's a kind of some performance limitation. So we developed some WaitIO file. The WaitIO file is very high latency, but using on top of some we have some very much of a file bandwidth. In that case, we increase 1 gigabyte per second up, even if some socket is only some 300 megabyte per second. It is. I have to say, here's this gray part is the WaitIO file performance, and this is a hybrid part. This is a hybrid better than WaitIO file because of using a random protocol. The random protocol is maybe much accelerated by WaitIO socket. It's a very low latency part, so it's included part of WaitIO hybrid. And here's I talked about some WaitIO application. Mr. Kengo already talked about, but I summarize. One is the WaitIO and UTMP application. Number one is real-time switch application. In that case, the real-time data processing plus simulation, and accuracy is used for data filtering and visualization, and also part of simulation and data simulation. And user gets some data from the JHPCN, which is a real-time ASCII sensor network. You can get some of the same data, the filtering accuracy, then go to simulation with data simulation in the Odyssey, and go back to some accuracy, some visualization thing. And second part is some WaitIO coupling application. Number two is a simulation, NICAM, and machine learning PyTorch coupling. This means used for atomic simulation plus machine learning, and accuracy used for machine learning using PyTorch, and Odyssey part is NICAM simulation. In that case, some simulation derived from the NICAM. It provides data from accuracy. In the accuracy part using machine learning and go to what the results. It's very fast and real time, so almost real bytes. It's very fast than that. And actually, we are going for a JHP project with heterogeneous coupling computing and JC use supercomputers because this kind of system very similar aim to the heterogeneous coupling computing. And we had some workshop and in this March, and we had a paper for the outset and the paper and some workshop on the advanced level global challenge application. I looked at some show of some results. And we had some target application with the JC and CA, and JC part in a three-cell simulation modeling platform, TSMP, and eigensolver, and brain animation simulation. And also CA in a selection in retard such comment main places and access simulation. And this is there not the time I took some brain animation simulation. And I finally will try to some portability comparison and deep system. Maybe a use complex data. They have some original application in the TCP and Maya, and maybe and target is our goal is to migrate this two kind of application to our reusability one using some HC open BDEC and compare the performance of the deep system reusability. And as you know, maybe deep system, well-known system type of some modular supercomputing architecture. And the modular supercomputing architecture, they have a prototype of the system. The system is named Deep. This considers four heterogeneous parting. One is a cluster module, is the only CPU part. And the second module is extreme scale booster. This is called a booster using some with the GPU. And the third thing is a scalable storage service module. This is the only storage part. And fourth part is a data analysis module. This is during the sum. We use some cluster module and booster module. And here's a deep system computation. Cluster has 15 nodes using some infinite EDR and also 2-second GEON. And booster part is almost same connected by EDR, but one socket GEON and some one V100. So we actually combine this time using WaitIO. And I talk some about target application Maya. And here's a Maya developed on RIC Aachen University. There are some geometry defined by STL, then also some mesh generator. And Maya is talk some several types of solvers with couplers. And this is used for biofluids, aerodynamics, and some high-speed flows and moving boundaries and particles. This is some many things. So when we think about the heterogeneous computing, we think about two kind of heterogeneous way. One is the time type A, this part. Because Maya is multiple solvers, and each solver can be shown using some original MPI and system A, and coupling part and the simulation part is written by WaitIO. It's very makes sense way. The other part is one solver is executed using some WaitIO for something. And we first target the just span solver and the post-processing mode. And here's some current development status. Type A part is initialization part of Maya. This kind of finished. And this Maya is this kind of coupling part is currently maybe implemented by a shared memory. So we need to migrate this shared library code to the WaitIO. So an initial part is finished. And type B is retrieval part of written by WaitIO function host, and starting to working on the GPU. And this kind of system A and system A on top of both of them ranks. So here's some of our early evaluation results. Here's a coupling using WaitIO and each solver using MPI. But this is only not a heterogeneous way, but only think some initial part comparison. And we use WaitIO basic one Odyssey, TOF, and the Intel bars. In this case, I talk about later because this part is the WaitIO bars and WaitIO TOF. And here's the result. This part is the Western Visual one, and this part is a deep system. And that's why Intel is faster and deep system faster. But in the running Odyssey, it's very scale. And most interesting part is up to 128 process in Odyssey. It's WaitIO is faster than future MPI. And also, it's difficult to see, but up to 30 processing on deep, it's WaitIO faster. That's because Maya code is very much used for MPI in place. It's not so tuned, but that's a bottleneck of the performance. Here's a type B version results. This is a coupling the WaitIO solver using WaitIO, but we use this test is we join some ARM CPU and Intel CPU both ways. And here's the result 120 processing 512 process. This part is let's say 6 64 process and accuracy of 64 process. And the 5 derivative, let's say the 448 process and accuracy part is 64 process because limitation of the number of nodes on the accuracy. As you can see, this is scalable using some and the results same. And this is a result of a real heterogeneous computing with Intel and ARM CPU in the same application. This is the first time. So next topic is some item this quantum project. This project is also presented by Kengo-san, and I'll skip over that. And in this system, we plan to develop two kinds of system software. One is QH scheduler over subnet, SciNet. SciNet is a Japan wider network on Japan, and some, for example, University of Tokyo and DKRC is connected by a 400 gigabps using some but high latency network. And in this way, we connect the centers in the SciNet, and we realize cascading some multiple centers use QC. And second different topic is H3 OpenVDX QH. It's a coupling and maybe some extension of the WaitIO and coupler. I talk of some WaitIO thing. And I talk of some WaitIO router. I can't even WaitIO use in the project side. WaitIO socket and it is not fast, but we need more fast and accurate way. So in the center, so we develop high performance communication using RDMA and zero copy routing. Because WaitIO, so we develop WaitIO bulbs and WaitIO top. And also I'm developing some WaitIO router for zero copy routing now user level. And among centers, we converting some single stream from RDMA and to multiple stream. And for performance, much RDMA and socket stream, because on the side it's a very high latency network, so it is better to use some multi-stream communication. And also it needs some security. For security reasons, so we implement some encryption and Scrum packet way to high performance and some security. So here's with our software architecture. I'm talking some API, and with our API is also same, and user interface and API. With our NVIDIA composite library and photon API and with corrected function. And also the two kind of where are the common style and socket and project style file system and that. And here is some performance result on the with above using some accuracy. Because accuracy has a full infinite HDI communication. And here's the result. Left side of the latest of the accuracy using a socket, it's on the 12 microsecond one way, but using with a bulbs, it's 1.3 microsecond like that. And for the right side of the performance, it's a megabyte per second. And the latest socket only have some 4 gigabyte per second, but using one stream in the 24 gigabyte per second, and with a 4 HCA 4 stream in the 96 gigabyte per second. So it's a scalable connection performance. And also we evaluate some with the bulbs on the material and the material. The material new test product with some NVIDIA 800 and 4 NVIDIA Infinite and 8 NVIDIA 400. In the scale almost same performance. RT performance is 1.7 microsecond one way, and using some much one stream using 48 gigabyte per second, using a 4 stream in the 191 gigabyte per second. It's very fast. So user can realize maybe 2 applications connected by or using for HCA in 190 gigabyte per second can communicate by advantage. And I have shown some for this part, but using some other communication. So usually other communication sender the right receive side, these are register memory and compatible. However, this is not a problem because the registration of the ML6 and with registration and release very well, high overhead because this is measured by a P2C application. It's one maybe registration is around some 27 microseconds, and for release in 18 microseconds is very high. Maybe TOEFL is better because they think about some this white can be used because some architecture part is always registered and getting some of TOEFL sterling address, it's very only user, it's very fast. And also the problem is some only known which memory needs to be registered when a communication process issue send receive. Because communication part personal user maybe executes the MPI. I send, I receive such kind of MPI process. That's the problem because so it's heavily dependent on the communication pattern of the application. So in number of processing areas can be registered as limited because some of over application, some of ML region, maybe commission library must maybe invalidate some older version because of overlapping is very confusing. So that's maybe so we develop some better register cache. And the second thing is but some limited, maybe Omnibus has some limitation of a number of register cache, bigger of 8,000, something like that. But I checked some of ML6, max ML maybe -1 because unlimited. Yeah. And actually, here's a H3 performance on the weighted buzzer. This is a very this version is the early stage of weighted buzzer. It is not faster, and here's a evaluated without rage ML release because in that case, communication in the way of send, register, and conversion, and send and finish and invalidating thing. So we register some emerging. It's a very high override. And here's the result in the sum of parts. And here's some inter MPI, and second is socket, and this is bulbs. This is it's slower than weighted socket. Nothing. And so we add some memory function to register. Because first registration after memory, whole kind of register for the memory. In this case, it's very faster and sometimes faster than socket. So we need such kind of overhead. This must be reduced more. So I took some with a top performance node. They say this is some this is socket performance. It's around 36 microseconds one way. However, using some WaitIO top in it's maybe 1/10 of some latency in the 3.4 microseconds. And on the performance, using some with a socket, it's only a 200 megawatt thing, and with a top using all up to 6.3 gigabyte per second. It's very 29 times faster with a socket. And we also some with this Python socket in that with the WaitIO, because some of quantum QC front-end software is using Python. So it's preferred to use a Python approach and combine the real application to the cluster. It's needed. And here's some result. We add some create some of class object, and combination buffer we use using a NumPy array, and some function is the same as C function, but limited. And also almost some create universe and initial part, and also rank and size, and also ICN, IRC right away. And the user can write this kind of way in a ping-pong program in the Python in the WaitIO part. And here's language sample. So user can two kind of application using some ping-pong in the MP application and some Python. Here's the last slide. Thank you for listening.
Okay, thank you very much.
Thank you.
Okay, thank you very much. And according to the program, we have a 15-minute discussion and summary. But usually it's some kind of buffer this time from that. So if you have any further questions, so I'd like to close the seminar. Thank you very much for coming. And so as I mentioned, next week, so we have another seminar, but it's a very special version and a panel discussion on in Japanese. And on December 9th, we have another seminar. So it's focusing on the machine learning and simulation. Okay, so thank you very much, and so see you next time.